Hello everyone. So today we're going to go over section 1.2, geometric series. So we are going to derive a rule to determine the sum of the first n terms of a geometric series, then solve some problems. Okay, example number 1, let's see here. Lisa is creating a family tree for her social studies class. Okay. Lisa has two ancestors in the first generation, Tom and Anne, and four ancestors in the second generation above. Okay, so if we were to organize this information into sort of a table, we'll have the following. So first generation would be two ancestors. Okay. Second generation, four ancestors. And then the third generation will be eight ancestors. Basically, it doubles every iteration. So, and then we will have the numbers 2 plus 4 plus 8. And then the next one will be 16, 32, and then 64, 128, plus 256, plus 512, and then plus 1024 in the 10th generation. So kind of omit some in between. So 9th generation, 10th generation. Okay. So if we are to add these numbers all together, we'll get 2046. And of course, we can look at these terms as a geometric progression. So this was 2, and then as the first term, and now 2 times 2 to the first power, 2 times 2 squared, and so forth. And here we have 2 times 2 to the 8th power, and then 2 times 2 to the 9th power. Okay. Right, so a geometric series, which is what we have in blue, is the sum of the terms of a geometric sequence, which is what's in green. The red values are the term numbers that we saw in the previous section. Okay, so obviously we don't want to be writing out the individual terms every time because that would be very time consuming. So we're looking for some sort of formulaic way to find these sums. Okay. But before that, some notations. We will let Sn represent the partial sums of the first n terms. So S1 will be just the first term. So in our case, the first term was 2. That's what we have here. S2 will be the first two terms added together, so T1 plus T2, as we have here. The first term was 2, and the second term was 4, and now series, so that would give us a sum of 6. And then, of course, in the third part here, the first term was 2, the second term was 4, and the third term was 8, and add them together, we have 14. So what that means for us is this sum right here, 2046, this would have been denoted S10, is the sum of the first 10 terms. Okay. So if we are to continue, we're looking for a formula to find the sum of the first n terms. As you can see here, the sum of the first n terms will be the first term, second term, and third term added together. And of course, instead of writing them as T1, T2, T3, we can write them as t1 times r, and then the third term will be t1 times r squared, and so forth. So this, of course, was term 4, t1 times r cubed, and so forth. So this would be the nth term, and this here will be the n minus 1th term. Okay, so we call this equation 1 to show how to find the formula for finding these sums of geometric series. Multiply both sides by r, so rsn is what we have on the left hand side. And now it's interesting because this will become term 2, right? t1 times r is term 2, term 3, term 4, and then these will be term n minus, sorry, this is the nth term, this is the n minus 1th term. Okay, so if we were to take Sn and subtract r times Sn, as we do in the third step, so subtracting equations 1 and 2, one was in red. Notice that these terms here, t2, t3, and so forth, they all disappear. Right? Actually, here we can see it. These terms are all going to be eliminated. So the first pair, this is term 2, term 3, term 4, and so forth, and they all get eliminated. And we are left with just t1 minus t1 times r to the n power. Then we can factor both sides, right? Notice that Sn minus Rsn has a common factor of Sn, which of course is just a number. So we have Sn times 1 minus r. And likewise on the right-hand side, we can factor out t1. And we have t1 times 1 minus r to the n power. Okay. So from there, if we divide both sides by 1 minus r, we have this formula. Sn is equal to t1 times 1 minus r to the nth power divided by 1 minus r. Now, the common ratio r cannot be 1 because 1 minus 1 will give us a 0, and then we will be dividing by 0. That doesn't work. Okay, so if the same process was used, but we subtract equation 1 from equation 2 instead back at the top here, we'll have a slightly different version of the formula. So this is what we did, and this is if we subtracted 1 from 2 instead. They both work. They're functionally the same. So we'll have Sn is equal to t1 times r to the n power minus 1 all over r minus 1. And again, they both work. Okay. So again, to generalize the result, we have in the box here, for a geometric series t1 plus t2 plus t3 and so forth, the sum of the first n terms is Sn is equal to t1 times 1 minus r to the nth power divided by 1 minus r. Once again, r cannot be 1. So we are going to apply this formula to a few examples. Let's see, example 1, determine the sum of the first 12 terms of this geometric series, negative 80 plus 40 minus 20 plus 10 minus 5 plus 2.5 and so forth. Okay, so again, we have our formula. Sn is equal to t1 and then 1 minus r to the nth power divided by 1 minus r. Alright, so what do we know so far? We know that the first term t1 is 80. We know that we want the sum of the first 12 terms, so n is 12. But we don't know r. But of course, we know from the last section that we can find r pretty easily. t2 divided by t1 is equal to r. So in this case, oh, sorry, I made a mistake. This is negative 80. that makes more sense. All right, so we will have 40 divided by negative 80, which of course is negative 1/2, and that's our common ratio r in this case. So now we're going to go ahead and use the formula. S12 is equal to negative 80, and then 1 minus negative 1/2 to the 12th power, and then divided by 1 minus negative 1/2. Okay, so notice here we have negative 1/2 to the 12th power, which is going to be a very small number. So in all likelihood, we are going to use a calculator for something like this. But of course, we can simplify the expression a little bit. So we will have negative 80, and then this just stays the same. The denominator could be simplified a little bit. 1 minus negative 1/2, of course, is just 1 plus 1/2. So we will have 3/2 in the denominator. All right, so if we use a calculator, let's see, 1/2. Okay. Okay, so the result approximately equal to negative 53.35, it looks like. Okay, let me just double check that. Oops. Oh. Uh-oh. That's okay. Oh, what's going on? Uh-oh. Okay. Yeah, so negative 53.35. Okay, so... Oh, I see. I made a mistake. Sorry. Okay, I see what I did. It's supposed to be 0.32. That makes more sense. Okay. Sorry about that. Let's try one more. See here, example number 2, we calculate the sum of this geometric series, 2 plus 6 plus 18 plus 54 and so forth. Okay, so in this case, once again, we're going to start with the formula. So Sn is equal to T1, 1 minus r to the nth power, all over 1 minus r. Okay, so in this case, once again, we know the first term is 2. The r value, we can just divide the first two terms. 6 divided by 2 is 3, so that's easy to find. Now, we don't know what what n is. Right? It doesn't explicitly state how many terms there were. So we have to find that out first. So we know that the nth term is equal to the first term times r and then n minus 1. So the nth term, and that is the last term in this case, is 118,098. And the first term, of course, is 2. and then r is 3, and then n minus 1. So we could divide both sides by 2, and we'll get 59,049 on the left-hand side. On the right-hand side, we have 3 to the nth minus 1th power. So just like in the previous section, we have to do a little bit of guess and check here. And we'll find that 3 to the 10th power is 59,049. So that would be 3 and then n minus 1. That, of course, means that 10 is equal to n minus 1. And we are looking for the sum of the first 11 terms. Okay, so now we know. So now we apply the formula as we would in the previous case. Sorry, as we did in the previous case. S11 is equal to 2 and then 1 minus 3 to the 11th power all over 1 minus 3. Now this one is a bit more interesting because we have 2 in the numerator, a factor of 2. And then 1 minus 3 to the 11th power, which is, of course, a large number. If we simplify the denominator, though, we get 1 minus 3, which is negative 2. So, as you can see here, the 2's eliminate each other. So this expression simplifies to be negative, and then 1 minus 3 to the 11th power. And that will give us, see here, 1 second. Okay, 177,146. Oh, that should have a dot above the equal sign in the previous example because we approximated, sorry, we rounded. Okay, so one more example for today. Example number 3. On the first day of the year, 2020, Warren puts $20 into his piggy bank. Warren decides to put in 10% more into piggy bank on the first of each subsequent month. How much will Warren have in his piggy bank on December 30th, 2022? Alright, so if it's 10% more, as we says here, then we have 110% of the last deposit. So in terms of a common ratio, we're looking at R equals to 1.1. Right, because it's 10% more than 100%, which makes it each deposit is 110% of the last one. So R equals 1.1. Now, T1 is $20. We know what R is. R is 1.1. And now we have to find N. So that will be 3 full years, 2020, 2021, and 2022. So that would be 36 months. Okay, so now we can apply the formula as we did before. So in this case, S36 is equal to 20, the first term, and then 1 minus 1.1 to the 36th power divided by 1 minus 1.1. Oops, that is really bright. There we go. Alright, so as You can see here the 1.1 to the first 6 power is going to be very hard to um, calculate by hand. So we're going to use a calculator in this case. And that will give us $5,982.54. So that's it. So that's how we um, derive the geometric series formula and how we apply it to find some sums. And that's it for today. So thank you for listening.